Hi, everybody. I'm going to do a quick explanation of what we'll call the multiple variable regression model. And we will think of it as being an extension of the single variable regression model, except now we'll think of other factors also explaining the outcome. So until now, we've just had a single explanatory variable, and we've said that the other factors are in the error term, the epsilon or the mu. And now we'll say, well, why not measure those other factors and include them as explanatory variables in the regression? So our model is now our outcome yi. So we have n observations. So we can think of indexing the observations. We can think of I as being an indicator for any observation in the population. So our model is that the outcome for any specific individual or person or county or firm, depending on what the entity of observation is a linear relationship between a variety of x's and that y. So we'll still have a linear relationship. So we'll have a coefficient beta 0, a coefficient beta 1, beta 2, beta 3, and we'll be estimating these coefficients uh, with the sample of data, and we'll be thinking that each um, uh, sorry, I'm changing my color here. Each x, so we'll have x1, x2, and x3. In this case, three explanatory variables. Each x represents a different variable. So this might be, in our Kenya earnings case, this might be the education level. This might be a dummy variable for the gender of the person. So it might be female if it's, and then being a 1 for female and a 0 otherwise. This might be the socioeconomic status of the parents of the person. So if you grew up in a wealthy household, your earnings might be high. We might think that that's a correlation or causal relationship that's worth exploring. So we'll think of this as our model. Three things are affecting Y: your current level of education, your gender, and the socioeconomic status of your parents. All of them are affecting the outcome Y, which is your earnings in the Kenya earnings case. There's still, of course, other factors. So we have mu or epsilon, the error term. Remember, mu and epsilon are the two symbols that are commonly used for denoting the error term. Um, so that would be our relationship. We can think of this also in the context of occasionally we mention our California schools data set. So in our California schools data set, we would have the outcome is the test score. Our explanatory variable is the student teacher ratio, the percent of English language learners in the district, and the percent of families eligible for free or reduced meals. So we have a set of districts, 1, 2, 3 listed here. We have observations for each one of their values for each of the variables, and those would be the three variables, x1, x2, and x3 we would include in the regression. And then we're estimating beta 1, beta 2, and beta 3. So to estimate these coefficients, we will choose coefficients that minimize the sum of squared residuals. So this is the same thing that we've seen before, the sum of squared residuals. The sum of squared residuals now is a little more complicated. It's still actual y minus predicted y, but predicted y now is using our whole model, our coefficient beta 0, beta 1, beta 2, beta 3, times each of the values x. We're adding them all up for all the observations in the model, just like in the single variable regression case, we'll get estimates then of beta 0 hat, beta 1 hat, beta 2 hat, beta 3 hat. The formula for these coefficients, these estimated coefficients, we're not going to worry about that, requires matrix algebra to be able to derive what the formula are for those coefficients. But we'll let R do that. Very straightforward. I'll show you a little later how to do that in R. We'll think about interpreting the coefficients, normally we interpret the coefficient as being our standard case as a 1 unit change in the x leads to or is associated with some change in the y. Now we're going to always add when we interpret a coefficient, we're going to say holding the other variables constant. So the effect of a change of x1 on y is b1 holding constant x2 and x3. The effect of a change in B2 on, B2 on Y is, sorry, let me say that again. The effect of a change in X2 on Y is B2 holding constant X1 and X3. And finally, the effect of a change in X3 on Y is beta 3 holding constant X2 and X1. In economics, we're very familiar with this concept of holding things constant. We call it ceteris paribus. Ceteris paribus means holding all else equal. We see it a lot in microeconomics and macroeconomics, holding other factors constant. What happens if you change one thing? What will happen to the equilibrium or to the outcome? So that's the same spirit here as we interpret these coefficients. For people who know calculus will interpret them as the partial derivative. So it's the partial derivative of x1 with of y with respect to x1 is beta 1. Implicitly, we're holding constant x2 and x3. Now, we'll still interpret coefficients for dummy variables as difference in means, but now we're going to have a more complex possibility. We can have multiple dummy variables for multiple categories. So, for example, the United States is divided into traditionally into the Northeast, the South, the West, and the Midwest. So West, Midwest, South, and Northeast. Those are the four regions, traditional regions of the United States. We could now include dummy variables for those regions. Are you in the West or not? Are you in the South or not? Are you in the Midwest or not? Are you in the Northeast or not? And we'll interpret the coefficient on the dummy variable as the difference between being in that place and what we're going to call the omitted category. So we'll see in a second, and we'll talk more about this in class, that if we have four regions, we can only include three dummy variables. So we always have to have a omitted category, a reference category. You know this in the case of a single variable regression where we had a dummy variable for whether you're female or not. The alternative was being male. We didn't have a dummy variable for whether you were male, female and male. We didn't have two dummy variables. We just had one. So we always include the dummy variables except for one category which we exclude. So in the case of a dummy variable that's just a single two category thing, we have a dummy variable for one category and not for the other. If there are four regions, we include three dummy variables, not the fourth. If there are seven kinds of counties, let's say, if we're thinking of the counties, then we'd include six of the dummy variables and not the seventh. So we always leave out one dummy variable for a group of categories. And that will be called the excluded category, and we'll interpret the dummy variable coefficient of each as the difference between being in that category that's included and the excluded category. We'll sometimes call that the reference category. So this is something you should definitely read about. Very important. Read about it in the chapter. Make sure you understand that. One other thing that we'll often think about is now that we have multiple coefficients, beta 1, beta 2, beta 3, for different variables, student-teacher ratio, percent English language learners, or the meal percent, or in the Kenya earnings case, a dummy variable for gender, a variable for education, a variable for parental household wealth, for instance. We sometimes want to compare those coefficients, beta 1, beta 2, beta 3, amongst themselves. But since they're all in different units, there's not really any comparison of their magnitudes possible. So we'll often standardize the coefficients by multiplying the coefficient by the standard deviation of the x and dividing by the standard deviation of the y. We'll sometimes call that a beta coefficient. We'll sometimes call that an effect size. And we'll interpret that as how many standard deviations in Y are changed when you have a one standard deviation in the X. So we can think of if, for example, in our Kenya earnings case, education was one of our X variables. The average education might be 5 years. The standard deviation might be 2 years. Earnings might have a standard deviation of $100. So a one standard deviation change in education might affect how many standard deviation changes in the Y. That's what our standardized coefficient, our beta coefficient, which we calculate with this very simple formula, that's how much it would change. And we can calculate that for each one of the x variables coefficients. So for 1, x1, x2, and x3, we can calculate standardized beta 1, standardized beta 2, standardized beta 3. Now they're in sort of comparable units. They're all in terms of a standard deviation change of the x variable. And so we can compare the coefficients more easily. Again, read the chapter. That will help you with thinking about that. We can also have logged dependent variables, and we can have, so we'll interpret them exactly the same way. We can have explanatory variables in logs. Uh, we can have outcome variables in logs. We can have outcome variable as a dummy variable. Then we'd interpret the coefficients as the change in the probability. So all of that stays the same. Uh, we will think about our confidence in our coefficients, but we'll think about it exactly the same way as we did in the single variable regression case. That is, we'll think about our coefficients as um, this is our confidence in coefficients. Well, our coefficients, our estimated coefficients will be random variables. Why are they random variables? Well, because we could have a different sample, we'd calculate a different estimated coefficient. So since they're random variables, we can say that if our sample size is sufficiently large, the central limit theorem says that the formula that we use to calculate these estimated coefficients is such that the coefficients will follow the normal distribution, centered on the true coefficient with standard deviation according to a standard error that we will calculate. Excuse me, still got a little lingering cough there. So we can then say that the t-statistic, the difference between the estimated coefficient and the null hypothesis that the coefficient's equal to 0 divided by the standard error, that will follow the standard normal distribution. So we can calculate for any t-statistic that we have for any coefficient, what's the probability of observing that t-statistic. If it's less than 0.05, we'll say we should reject the null hypothesis that the coefficient's actually equal to 0. So all that is exactly the same. Our assumptions for the validity of sorry, these are assumptions for the validity, not quantifying the sampling uncertainty. Wrong title here. Our assumptions for the validity are the same. The expected value of the error term, here I have mu, but epsilon would work just fine. The expected value of the error term, subject now to all of the coefficient, the explanatory variables, is equal to 0. So that's our same assumption that now we have, in this case, k explanatory variables. There's still other factors there. Our assumption is those other factors are not confounders. So we have no confounders. We have no other factors that aren't included in our regression that are correlated with the x variable and also causing the outcome variable. That will still be our assumption. We'll still assume that our sample observations are drawn from the population and are independent and identically distributed. So that it doesn't hold if there's time series, right? That's our main case in time series. Our observations are not independent of each other because what happens this year depends on what happened last year. So our observations aren't independent of each other. We'll still assume that there are low likelihood of large outliers. We'll also assume that there is no perfect multicollinearity. So we'll assume that if we have four dummy variables, for example, uh, north, south, east, and west, those four dummy variables are linearly related. So the value for west, for example, is equal to 1 minus south minus northeast minus um, Midwest. So because you have to be one of the four, and you can only be a one for one of them. So the dummy variables are linearly related. We can't have four variables that are linearly related in there. We can't have a set of variables in the regression that are collinear, that are linearly related. So that's why we always drop one of the dummy variables. There may be other situations, though, where we have perfect multicollinearity, where we have two variables that are linearly related. For example, we could think of you include the variable for temperature in Fahrenheit, but then on accident, you also include the variable for temperature in centigrade. And if you know, there's a linear relationship between centigrade and Fahrenheit. You take centigrade, multiply by 9, divide by 5, add 32. That's the temperature in Fahrenheit. So there's a linear relationship between those two. If you included both of them in the regression, you would have perfect multicollinearity. And perfect multicollinearity means dividing by zero when you're doing the calculation of the estimated coefficient. So R can't do that. So R will automatically drop one of the collinear variables. Also, intuitively, if you have collinear variables, we can't interpret the coefficients as being what happens if you change one and hold the other one constant, because the two variables are collinear. You can't hold the other one constant. They vary together. If temperature in centigrade goes up, so does temperature in Fahrenheit. You can't say what would happen if temperature in centigrade went up, but temperature in Fahrenheit stayed the same, right? That doesn't make any sense. So that's the idea of perfect multicollinearity. Just is an assumption that we have to have. And it's rather obvious, but sometimes you'll encounter subtle cases where you don't think that two variables are linearly related. And then it turns out, for reasons that you didn't know, perhaps, or were not obvious, that the two variables are linearly related. Um, so that's our discussion. We'll talk later in class about imperfect multicollinearity. Um, and I think, let me just erase all this stuff. And I have a couple more things to say in this very quick intro video. Um, and where did I want to go? Yeah, I need to go here. Um, we Let me talk about goodness of fit measures. We'll have two a new formula for goodness of fit. So we'll still have the standard error of the regression, but now we're going to subtract the number of regressors here in the denominator. So it'll be n minus k minus 1. And K here is the number of regressors that we have in the denominator, so in the as explanatory variables. So if we had earlier, we had x1, x2, and x3, so K would be equal to 3. So we'd have n minus 3 minus 1. And we'll still have the sum of squared residuals in the numerator. For r squared, this is our formula for r squared. The two variations, explained sum of squares divided by total sum of squares, or 1 minus the sum of squared residuals divided by the total sum of squares. Now we'll have something called adjusted R square, and adjusted R square will be this formula. And notice the difference. We're taking this term and introducing it before sum of squared residuals and total sum of squares. So n minus 1 over n minus k minus 1. So small adjustment to this formula. What does this do? Well, the R squared formula, if you think about it for a little bit, and we'll again talk about this in class, whenever you add an explanatory variable, R square automatically goes up. And the reason for that is that adding an explanatory variable always improves the goodness of fit or leaves it the same. In other words, when we're choosing coefficients to minimize the sum of squared residuals, calculus problem, remember, we're choosing the coefficients to minimize the sum of squared residuals. If we add one more explanatory variable to that, R will always optimize by choosing coefficients that minimize the sum of squared residuals. So it can always have the option, right, in doing that function of having the coefficient on this new variable be zero, in which case the sum of squared residuals would be exactly the same as the regression without this new variable. That is, if you add this new variable, R, when you're minimizing, choosing coefficients, you could always decide in the minimization process, I'll have this coefficient be zero. If the coefficient is zero, then the minimum sum of squared residuals will be the same as it was before. So the coefficient would either be zero, but if it's not zero, if it's any other number, because you're minimizing the sum of squared residuals, the sum of squared residuals has to be lower than it was before. Before meaning when you didn't have this new variable. So in some sense, you're relaxing a constraint. Relaxing a constraint means you can minimize even further. And so the R squared will go up because sum of squared residuals will be smaller than it was before. So that's a downside because you might be tempted to say, oh, I should just add a whole bunch of variables, even if they have no reason at all to be in my regression, because my R squared will go up. So the adjusted R squared penalizes you for adding more variables. Adding more variables makes this denominator a smaller number, which makes this a bigger number, which makes what you're subtracting from here a bigger number. So adjusted R square could actually go up if you add a new variable that has very little explanatory power. Adjusted R square adjusted R squared will go down instead of up. So R squared will always go up, but adjusted R squared could go down. So it's a goodness of fit measure that penalizes you for adding variables that shouldn't really be in the regression. So adjusted R squared is a nice new measure of goodness of fit. You should, think about its properties and look for it now when we run regressions and look and see whether there's differences. In many of our cases, there'll be third decimal place differences between R squared and adjusted R squared, but it's something to be looking for in the regressions. I think I will, yeah, I wanted to go back and there's one more thing I wanted to do. This is an excerpt from Stock and Watson's textbook. And these are 4 points to think about in R square. Increases in R square don't always mean that the new coefficient is statistically significant. A high R square doesn't necessarily imply a causal relationship. A high R squared doesn't mean that there's no confounders. There could well be confounders. And a high R squared doesn't mean you have the sort of best regression, or a low R squared doesn't mean you have a bad regression. So these are just 4 points that are worth mentioning and repeating. The goal of regression analysis is not to have a high R square or high adjusted R square. The goal of econometrics is to test the individual coefficients of the variables of interest. So again, I want to encourage you to read the chapter on multiple variable regression. And don't think that just this very quick summary that I've given is enough. There's a couple. We also remember our other assumptions about multiple regression or about regression analysis, that it's a linear relationship and that there's causality from the x variable to the y variable. Those are still assumptions. I didn't mention them earlier. So I'll have a little bit more, another video with R in a little bit. So see you in class.